Hello guys, let's understand the concept of red black tree. Red black tree is a balanced search tree data structure. So I can say a red black tree as a balanced search tree. It is a balanced search tree data structure. Now we have already studied the balanced search tree as BST, that is binary search tree, and AVL trees. So in BST there is a problem when a sorted sequence is given. If a sorted sequence of elements are given, then the BST generally either left skewed or right skewed. So the balance is not there. It means the operation will take order of n time because the height of the tree will increased in number of elements. Okay. So to overcome this problem, AVL tree will come, which will introduce the concept of rotations. By the rotations, the height of the tree is balanced, and it will give the operations in order of log n time. So AVL tree is the efficient data structure because it will maintain the height of the tree while we do the insertions and deletion operation. Now whenever in any application, if the insertion and deletion have the occur in frequent amount of time, then the AVLs are not so much efficient. So the extension of AVL tree, that is ragged black tree, came into picture, which will introduce the concept of recoloring along with the rotations. So it will add the rotations and recoloring concepts in order to balance the search tree. So by the recoloring, we can reduce the number of rotation in the search tree. So it will reduce the number of rotations in the search tree. So we have different type of search other search trees are available, like skip lists are there, which can be used as a balanced search tree, and some tribes are there, or many other data structure like 2-3 trees are there, or we can have 2-3-4 trees, and so on. Okay, these are many type of data structures are available. Now in this lecture we will focus on red black tree. So red black tree is a binary search tree with one extra bit of storage. So because it will introduce the concept of coloring, for that it will add one extra bit of storage per node, and that is known as color of a node. The color of a node can be either red or black. Okay, so the operations designed on the arbitrary guaranteed that the height of the tree would be in order of log n. That's then only it can be efficient balancer tree. Okay, now arbitrary follows some of the properties which are as follows. First is every node is either red or black, as we have discussed earlier. It will introduce the concept of recoloring. Every leaf is a null pointer. So in arbitrary there is another concept is added, that if a tree is given as, suppose this is a tree with the information 8, suppose 5 is here, and suppose 9 is here. Now this tree have leaves with null pointers. So we have some null pointers. Suppose here it is 10, then this 10 also have some null pointers. So it is divide your tree into different types of node. So the one is the root node, which is the uppermost node. Other is, these are the internal nodes, 5, 9 and 10. These are the internal nodes. So all internal nodes have some key value, and then other leaves are nil nodes. Nil nodes means the node without key value. Okay, so this whole tree can also be represented as suppose this 8, 5, 9 and 10, because all have nil leaves, so these whole pointers can be combined in one nil of tree data structure. So in some books you can see this type of representation of arbitrary. So the idea is every leaf is a null pointer and the color of this leaf is considered as black. Okay. Now third point is, if a node is red, the both children are black, so we cannot have two consecutive red nodes on a path. Fourth one is, every path from node to descendant leaf contains the same number of black nodes, and that is black height. Means if we count, suppose I will draw a red black tree here. Suppose the same information is, suppose it is 5, and here it is 9 and 10, and suppose here it is 6. Okay. Now suppose this is your black node and this is your black node. Okay. So now the color of these two nodes must be red in order to satisfy the property of red black tree. So I make the node of this color as a red and the node of this color as a red. Now what would be the black height? So and let me link this one. So this is a sentinel node, this is also sentinel nodes, and this tree also have sentinel nodes, and this tree also have sentinel nodes. So the black height is the number of black nodes in this path. So the number of black nodes in this path is 1. The number of, so we cannot, in black height we are not including root node. So the black height of this path is 1. The black height on this path is 2. The black height of this path is 1. The black height of this path is 2, and from this path is also 2. So this is not a red black tree because the black height is not similar in all the paths. But if I change the color, suppose I make this 9 as a black and make 10 as a red, so consider double oval as a red. Also I make 5 as a black and make this color as a red. Now so again I calculate the black height at each path. So I delete this black height. Okay. Now again I write the black height on each path. So the black height on this path would be, so this is black now, it is 2. The black height on this path would be 2. The black height on this path is, so this is one black node and another sentinel is also black node, 2. This is red node, this is not counted, 1, 2. Now it is a red black tree because the black height on each path is same. Now it is become a black red black tree. Okay. So the every path from node to descendant leaf contains same number of black nodes, and so if I include the root node, the black height would be 3. But in order to, the black nodes would be 3, but in order to find out the black height of a tree, the root node, color of root node is not included. So black height of this tree is 2, and the color of sentinels are included in black heights. Okay. And fifth most point is, the root is always black. So the root color of root node is always black. Okay. So next is okay, this is about the properties of arbitrary. Also one more thing is that let me delete this one. Excuse me. So one more thing is that the height of arbitrary, the height of arbitrary, the height of the arbitrary h is always less than or equal to 2 log n plus 1. So or we can say that order of log n. The height is always in the order of log n, and it is always less than log 2 log n plus 1, where n keys are there, n keys information are there. The proof of the same can be seen in the Corman book, so you can see, refer from that. So height of the arbitrary is always be order of log n. Okay. Now the next thing is, on arbitrary there are various types of operations can be performed. So there are two types of operation on any data structure. One is querying operation. So if someone want to query something like to search an element, or finding minimum or maximum, okay, or successor in the tree or predecessor in the tree. So these type of operations are querying operation. Another operation are called update operation, in which we have to modify the data structure, and this type of operation include insert and delete operation. So now we will see how we can insert an element into the arbitrary. So all type of querying operation in arbitrary will take order of log n time, due to the height of the arbitrary is order of log n. So in order to query it, we need to in worst case we need to explore the all of the height of the tree. So in the arbitrary insert procedure, if any red black tree is given, then and any information is insert, we want to insert any new node in the given arbitrary, then first, because it is a kind of binary search tree, so what we do, we insert the element according to the BST insertion. Suppose if you want to insert the value 4 in this tree, so this value I call this arbitrary insert procedure on this node, on this tree T with information 4. So first take a pointer y which is pointing to some nil of t, then make root is pointing by a pointer x, okay. Then let me change the color so that it is more clear to you. Suppose this is the color, okay. Now while x is not equal to nil of t, so we will check regularly whether x is nil of t or not. If it is not nil of t, yes, make pointer y which is pointing to same node as x, check whether key of so here suppose we need to check whether key of z, so key of z means 4 is less than 11, 4 is less than 11, yes, move to the left. If it is yes, move to the left. So x is moved to the left part, here x is moved to the left part. Again check whether x is equal to nil of t, no, x is not nil of t. Again check whether key of x, so before checking we assign y here, and check whether key of x 4 is less than 2, no, so condition false, that's why x moved to the right part. Then update the y pointer and check whether key of x means key of x is now 7, key of x 7, and check whether 4 is less than 7, 4 is less than 7, yes, 4 is less than 7, it means it will go to the left part. So x is here, y also updated because x is not equal to nil, then x and y is pointing to both of the on the same location. Then again check whether key of z means 4 is less than 5, means key of x, so key of z is less than key of x, it means yes, it is true. So x is now pointing to left part, so x is now pointing to left part of this tree. So these are some sentinel nodes and x is pointing here, so x is pointing to left part. Now again check while x is not equal to nil of t, and while loop is false here because x is now pointing to nil of t. So I make the parent of z as a y, so I make parent of z, so y is pointing to 5, yes, so 4 is inserted here and the parent of 4 would be 5, okay. Now check whether y is nil of t, no, y is not nil of t, so condition false. I directly jump to the line number 14. So this condition is when we have only one node in our tree, and then it is the condition is y is equal to nil of t. And then so in line number 14 we make the left and right of 4 as a nil by these two lines and make the color of z as a red. So make the color of a z as a red. So I make it the color of z as a red. So it is a red color, it is also red color. This will violate the condition property number 3 of the arbitrary, that is no two consecutive nodes have a red color. So this property is violated, so we need to run the arbitrary fix up procedure to solve this type of problem. So let's see what is arbitrary fix up procedure. So this is the my tree in which the red nodes are here it is 2 is red node, 15 is red node, and here 5 is red node, and 8 is also a red node, and I insert 4 at the left hand side which is also red. So I just change the ink here, it is 4 which is also a red node, and these are the sentinels attached with the each of the node. So the sentinel is attached with the each of the leaf nodes, okay, and 11 is a root. So this is the tree after insertion of 4, because here the property is violated. So I run the fix up on tree T with node Z. So Z is here, okay. So fix up procedure says that we need to check the color of parent of Z while current of, so the loop is executed, while loop is executed until the parent of Z is red, okay. So until the parent of Z is red, so whenever it is black, when it is black the while loop is exited. Now because it is red, we go into the while loop and check whether parent of Z is at the left hand side or right hand side. So it is a left hand side of its Z's grandparent. So yes, it is in left hand side. Then we check whether y which is point, we assign y. So I just change the color, sorry. So we assign pointer y here, which is uncle of the Z. So if the color of the uncle is red, this is case 1. When the color of the uncle is red, we just need to do the recoloring. So in case 1 only recoloring is done, there is no rotations, only recoloring is done. So what we do, we just recolor the number of nodes. So I just remove the colors of existing node first. So I remove the color of this one, color of this one, and color of this one, okay. So now I make the color of, first thing I make the color of parent of Z. Color of parent of Z is red, make this color as a red. Color of Y means this color is also, sorry, make this color as a black. Color of Y also black, and color of grandparent as red. So make the color of grandparent as a red. So always always see the algorithm and do the changes accordingly. So in the first case, what we do, we just make the color of a parent and a uncle as a black and current of grandparent as a red. So only recoloring it, then our purpose is solved. Then what we do, we update the pointer Z. So Z is now pointing to grandparent. Z is now pointing to grandparent. So after case 1, Z is now pointing. So now Z is at here. So after case 1, Z is pointing to the grandparent. After that, we check whether this grandparent is at the right of its parent. So yes, it is at the right of its parent. So update the Z let me select the ink. So I update this Z here, Z is now updated, and I apply the left rotation. So after the left rotation, the tree will become 11. So we apply the left rotation on the node. So here 7 is come up, 2 will go at the left hand side and 1 will go here. Then at the right hand side of 7 it is 8, and 5 and 4 will be added to the right hand side of, so it is BST left rotation or AVL left rotation, you can say that. Then it is 14 and 15. So let me color all the nodes. So first take the black color. So black color node is here, it is black. Now 2 and 7 are red nodes, 8 is black node, 5 is also a black node, 1 is also a black node, and here 14 is also a black node. Then I color the red nodes. So in my tree red nodes are 15, and 7 and 2 are the red nodes. Okay, 4 is also a red node. Now after rotation, the pointer Z is here at the 2. So now I am at line number 12. So I check whether I will make the color of parent of Z is black and color of parent of Z as a red. So I just change the color of the two nodes. So I have to change the color of these two nodes. So the color of the parent is black, and the color of the grandparent of Z is red. So I make this color of 11 as a red. Then I have to right rotate on the parent of Z, means I have to right rotate this grandparent. So after rotation the tree will become, so after rotation, because I need to right rotate, 7 will be the root at right hand side, 11, 14 and 15 is there. At the left hand side 2 and 1 would be there. Then 8 is at right and left of this node, so 8 is inserted here, 2 is inserted at the same position where they was earlier. Then I color these nodes. So the color of the nodes would be, first select the black color. So the black color nodes are 14 is a black, and 8 is a black, 7 is black, 5 is black and 1 is black. Then color the red nodes. So the red nodes are, 15 is a red node, then 11 is also a red node, 2 is a red node, and 4 is also a red node. Okay, now check whether the black after this 15, if so this is the case when this Z is at the right hand side of its parent. So if the case 2 here, in case 2 Z is at the right hand side of its parent, it would if it is at the left hand side, we will exchange the same algorithm and do the same. We need to if we left rotate something, so we have to right rotate, or in place of right rotate we need to write here left rotate. Okay, so we will reverse the process accordingly. Then after that, color of root of t. So this is my root, color of root of t, I make this color as a black, it is already black. So now this is a final arbitrary. So let's check whether what is the black height. So it is 2. If I consider the sentinels, it is 2. From this path it is also 2, from this path is it 2, and from this path also it is 2. So from all the paths the black height is 2. That's why this is, the tree is balanced now. So this is how we can insert an element in a arbitrary. Thank you.